Ready to get started. Okay. Get to just about less than a minute here in a couple. Okay, here we go. So hello everyone. My name is Reed Malevich from Sandia National Laboratories, and today here I am chairing the session on synthesis and reverse engineering. So we have a great lineup of papers here to present today. It will take 5 minutes for each presentation. If you have questions, put them in the chat. If there's time to get to them during the presentation, then if it's short, then yes, we'll bring them up. But otherwise, we can save them to the end for the discussion. So first up on my list here, I have learning to find usages of library functions and optimized binaries, presented here by Tawfiq Ahmed.
Thank you. So let me share the screen again. Can you see my screen?
Yes, I can. It's great.
Okay, thank you. So today I'm going to present our work, Learning to Find Usages of Library Functions in Optimized Binaries. I'm Tawfiq. I'm a fourth-year PhD candidate from UC Davis. This work was done by me, my advisor, Professor Prem Kumar Devanbo, and Ananta Shapsan. Library function usage is often hard to find in optimized binaries. Optimization transforms the original source code into something that is entirely unrecognizable. Understanding the binary's behavior or reverse engineering is a time-consuming task, but a very important one. Binaries can be harmful or guilty of intellectual property theft. On top of that, this optimization makes the reverse engineering task difficult by making the function call inline. So let's look into this example. Here we have a two-code snippet. On the left, we have a function that is written in C, and on the right, we have the decompiled version of that code that is generated using Ghidra. So if you look into the original source code, there are four function call, but in the decompiled version, we can see that the Ghidra recovered three of them. There is one missing function here, string copy. So we propose a deep learning based approach function that will recover this missing string copy for the reverse engineer and help them to understand the behavior of the binary as well. On this goal, we propose an automatic leveling scheme to generate dataset of binaries labeled with the actual function usage. And we also showed that our model function combined with Ghidra achieve state of that performance in function called recovery task. So this is a general pipeline for this decompilation task. The complete process starts with the source code, then the compiler do the optimization, compile the program and give us the binaries. And these binaries are the real world starting point for the reverse engineer. So reverse engineer usually takes these binaries, use some state of the art tools like Ghidra, IDEA Hex Pro, and produce this assembly and decompile code. And our tool Frankie can work on top of this decompiled program and find out the missing function like string copy for us. So building C project is difficult. So we use a Buxom that came in 2019 to build a large number of C projects. We have to modify Buxom a bit because the objective of Buxom and our paper is a bit different. And Buxom was not um, originally developed to build C projects. So, but there are several steps that Buxom does for us. It identifies the right Docker container that a project usage, then download the projects into the container, and also it install the it does the most important task, install the dependencies. And we build the project using its script and the Travis configuration of the project for our dataset. So now we have built the data set. We use the decompilation tool and produce the decompiled version that you can see on the left side of the screen. And we have this decompiled version and original source code, so we can compare both version of this original source code and decompiled version and see which functions are missing there. And after finding those functions, we introduce some indelible markers into the original source code. We build the project again and decompile again. And after the second decompilation, we will get something like what we can see on the right side of the screen. This is the same function, decompiled version of the same function, but we have an information here like the memset function is inlined here. So we can generate the training data set from this marker version of this decompiled code. So let me present the results here. So this Funktree is not directly comparable with Ghidra or Hextray because we trained Funktree to find the missing function that were missed by Ghidra. So we combine the results of Funktree with Ghidra and then compare it with Ghidra itself and Hextray. And we found that for all optimization level, our this combination of Funktree and Ghidra achieve the maximum X score for recovering library functions, and also together these two tools together achieve retrieve maximum number of unique functions. So let me summarize the contribution of this work. We propose an approach to build C-based project on a large scale. We showed that pre-trained models are beneficial for inline function recovery tasks, and combined with Ghidra, our tool outperformed Ghidra itself and Hextrace on library function recovery tasks. So thank you.
Great presentation. Yeah. So the next one that we have up is dynamic update for synthesized GR1 controllers. I believe Matan Yosef is presenting today for that.
Can you see my screen?
Let's see. Yes, we can.
Yes.
All
okay.
Right. Go ahead.
So hello, everyone. My name is Matan. I'm from Tel Aviv University. And in the next 5 minutes, I'll talk about dynamic update for synthesized GR1 controllers, which is a joint work with Dr. Gal Amram, Professor Shahar Maoz, and Dr. Itai Segal. So let's start. So we'll start with a bit of motivation. Let's say we have a robot and we want it to perform a set of tasks specified by spec 1. So this task can be patrolling some rooms or maybe take an object from one room to another. So we synthesize the controller C1 and the robot executes it. Now, after a while, the first set of tasks is no longer relevant. For example, maybe one of the rooms in the patrol is now under construction. So we want the robot now to perform a new set of tasks specified by spec 2. We want it to update its specification and start execute a new controller, C2. But we don't want to stop the execution and reset the robot completely. We want to update while the execution is still running. So our goal is to find an update strategy. What is an update strategy? So first, all the computation involved should be made while C1 is still running. Once they are finished, we are still allowed to take additional steps in compliance with spec 1. But eventually, we should reach a state S from which we can smoothly and without stopping start taking steps only that satisfy spec 2. We also require that the switching state S will satisfy some switching condition. For example, maybe we want the robot to make the switch only when it is located in a certain room. So what is the dynamic update problem? So given game structures and a switching condition, we want to compute a set of states W, which are all the states and only the stage from which we can update. And an update strategy is sigma, like we saw in the previous slide, that will take us there. And of course, maybe there are no such W and sigma. In this case, we want to determine so. So our solution is divided into two parts. First, we want to compute the winning region for the new specification W2 and a controller C2. Then we want to compute a bridge controller, which is a controller that will lead us from the current state of the execution into W2. So what is the bridge computation look like? It is divided into a few steps. First, we define the legal transition during the bridge. Then we use a classic reachability algorithm, and using backtracking from W2 with fixed point iteration, we find the set of states W, which are the set of states from which we can update. And while we're doing so, we also calculate the bridge controller B that will take the system from W to W2. Below you can see a drawing. So we start from C2, from B0, and then we start the backtracking. And each iteration, we find more and more steps from which we can update until reaching a fixed point. Once we're finished, we see that the current state of the running controller, S0, is covered in the bridge controller we computed. So we can start executing the bridge until reaching C2. We also created an optimization which communicates with C1 during the fixed point iteration. On each iteration, we can check if the current state of the running controller is already covered in the bridge we computed so far. If it is, we don't have to complete the bridge computation, and we can start immediately executing the bridge we computed so far. This can shorten the bridge computation time, shorten the switching phase, and also increase the chances for successful update. Here you can see an example. So we start the backtracking, and once we're finished, once we're in B3, we see that the current state of the running controller S0 is already covering the bridge we computed so far. So we don't have to compute B4, and we can start immediately executing the bridge until reaching C2. So we have a few research questions in the evaluation. First, we wanted to compare update strategy synthesis with standard GR1 synthesis and see what is the added cost of the supporting dynamic update. Second, want to see how many steps does it take for the bridge controller to complete and activate C2. And third, we wanted to check if our optimizations improve the performance in terms of running time and switching phase length. Our corpus includes thousands of specifications of 3 families: moving obstacle evasion, prioritized arbiter, and job scheduler. Here you can see the results of the moving obstacle evasion. So without diving into details and numbers, we can say that we saw that the bridge computation time is in the same magnitude with GR1 synthesis, so sometimes even less, that our optimizations cut the bridge computation time and switching phase length in half or even more. So that's it. We welcome you to read the paper again and dive into details, and we thank you for listening.
Great. Fantastic work. I love it. All right, so next up here, we have push button synthesis of watch companions for Android apps. Hongli will be presenting for us.
Okay, can everybody see this?
Yes, we can.
Okay, cool. Let's get started. Hello, everyone. My name is Tong from Nanjing University, China. Today, I'm going to share with you a very interesting program synthesis application called Jigsaw. Let's port your favorite app to a smartwatch. Indeed, we are interested in this application because there are so many watches today, but there are not that many apps that we can use to take their convenience. Indeed, this forms a big gap between smartwatch and their convenience. And what we'd like to do is to try bridging this gap by doing something work like app synthesis or companion synthesis. And this is our big picture. On the left, we have the app. On the phone, we have the app. On the watch that we'd like to synthesize. And our work is works like doing a jigsaw. First, we disassemble the app to many widget pieces. And from all of these, we just select part of them and then migrate and recompose them on limited watch screen. In this process, actually model the companion synthesis problem as 2 sub-problems. First, we have to decide which widgets should be selected. Second, we have to decide how to compose these selected widgets on a limited screen. And formally, we'd like to find 2 functions, f and g. Firstly, we directly drop those widgets. That f returns false. And then for f returns true, we have function g to decide the exact position on the watch screen of every selected widget. Indeed, it's hard for machine to know which widgets to migrate from scratch, but the UI design follows spatial locality, so we can learn from examples. Like here, you may notice all the digital widgets have the same parents, right? All the operators have the same parents. So if we know none is an example, we can learn we should select all the digits. And if we know plus, then are operators. And if we know both non and plus, then we know maybe we should select all of these because they have the same grandparents. Yep, that's the idea behind our function f, which we call widget selector. It can select properly matching widgets level by level along this tree. Like this one is our widget selector. It works like an XPath or CWI selector. And our goal is to synthesize such a selector that can select all positives and reject all negatives from these examples. And indeed, for this goal, we applied version space algebra to do this synthesis. And in here, the version space of our example widget is a set of widget selectors that can select the specific widget. And having this variance basis, we just intersect the variance basis of all positives and subtract the variance basis of negatives, and we can get a final variance space. Since there may be multiple selected in the final variance space, we have to rank them and get the optimal one as our function f, and like this one. As for the function g, we take a very sophisticated approach by modeling the limited watch screen as a m times n grid, and our goal is to put every widget in a single cell like this one into O. And for this goal, we just collect the position relations from the form, like widget 9 should be to the left of 5 and to the top of 5. We collect a set of such constraints and fed them to a set solver to get their exact position on the watch screen. All right. In the summary, our companion synthesis is separated as two separate problems. First, we use f to select widgets, which we model as a selector. As second, we use function g to determine the exact position of every widget on the limited watch screen, which we model as a grid. And we use variance space algebra and constraint solving for the two sub-problems, and then we combine them together to get our final companion. Yeah. And here we show some example of our synthesized companions. You may notice some successful ones looks, yeah, they looks good, but failure ones also look not that good. Like in here, it selects a widget that we don't want to migrate, and here it just fails to render a web view.
Yeah.
Yes.
Oh,
all right. Today,
5 minutes. Going to finish up.
Today we displayed an interesting program synthesis example called Jigsaw. We don't mean to solve the app synthesis once and for all. Is that it still has many limitations, right? And there's a long way to go. But we hope Jigsaw at the start of this direction will attract more research attentions. Yeah, that's all. Thank you very much.
Great presentation. And really, seeing is believing with this. Being able to see these outputs and show that they're working is amazing. So that's great.
Thank you very much.
Yeah.
Just try it.
So right here, the next one we have up is also named Jigsaw, though a different paper. Jigsaw: Large Language Models Make Program Synthesis, and our presenter here is Naman Jain. If you want to take it away.
We can't hear you. The microphone is off.
Sorry, can't hear you yet. I think you're muted. That would be why.
Okay, can you hear me now?
Yes. Now.
Thanks a lot. Yeah. Hi everyone. I'll be giving a talk on Project Jigsaw, where large language models meet program synthesis. I'm Naman, and this is joint work with Skanda, Arun, Naga, Suresh, Sriram, and Rahul at Microsoft Research India. So you might be aware that nowadays we can generate code snippets from these large language models like GPT-3 Codex. So basically, you just give them some natural language description of some intended task, and they'll generate some code for you. However, this code will only be hopefully correct. And this is because these models do not understand syntax and semantics of the programs, and they do not provide any guarantees. So this is why GitHub Copilot website itself mentions that the code suggested should be carefully tested, reviewed, vetted, like any other code. And even if we fine-tune these models, build bigger models, build better data sets, the vetting process is a necessity, and the burden falls on the users of these models. So what can we do to help them? This is where the Jigsaw hypothesis lies. We believe that if we augment these models with guardrails based on program analysis and synthesis-based techniques, we can automate some of this vetting and make the users more productive. So let me outline the Jigsaw vision for you. So we have this stacked architecture like this. And at the start, you'll see some inputs. So you see natural language. But apart from natural language, we also take some form of additional specifications. These may be input-output examples, tables for table manipulation tasks, or they might be as abstract as static analysis specifications. Next, we take these inputs, primarily the natural language input, and we pass them through a pre-processing module, which will build the correct context prompt for few-shot learning for these models. So it will find relevant examples and give them as input to GPT-3 or Codex or any other language model, because we have a plug-and-play architecture. You can use any new model if you want. So once these models generate some code that might be correct or incorrect, we pass them through our post-processing module. This is where the program analysis or synthesis magic happens. And here we try to fix this code and repair by generic program repair strategies. And then we pass this to the user. So we'll let them know if we found the correct solution or we didn't find the correct solution. And the user can, in case we didn't find a correct solution, user can generate some fix. And we also are able to learn from this user feedback and improve our post-processing module. So let me show this with an example. In our paper, we focus on pandas table manipulation tasks. And let's see how a user would use a language model without Jigsaw. So you might write a query, remove substring name colon from column C of data frame. So if you want to remove some prefix in the column of a table, and you'll pass it to the model, and the model will generate some code. However, when the model generates some code, it won't even tell you whether the code is incorrect or correct. You'll have to understand what's happening and maybe even try it on some input-output example to see what happens. Instead, with Jigsaw, you'll pass the input-output example as additional specification to the model. Now, when you pass it through Jigsaw model, there are two cases that are possible. The first is that Jigsaw model already produces the correct solution. In this case, we can inform the user that based on the input-output specification, this code is correct and would probably work in your case. The other case that is possible is that Jigsaw model is still not able to find the correct solution. So what can we do here? In this case, the user will inform the user that we weren't able to find a correct solution, but this might be a potentially useful starting point. The user, after some hit and trial efforts, might be able to find the correct solution. And we learn from this user interaction. We'll use the user fix code, and we'll learn from this feedback. So in future, if someone else asks a similar query, maybe with some different variables, different data frame names and column names, then we'll still be able to use this user interaction and improve the performance for the future user, and thus improve over time. So finally, let me outline our results. So we built a multimodal robust synthesis system for large API with more than 100 functions, which is pandas. And our key insight was we found that different language models were failing in similar ways. So they were making mistakes like mistakes in variable names, mistake in arguments, some mistakes were repetitive mistakes which were lying within a small AST threshold. So based on this insight of failure, like common failure modalities, we built generic program repair strategies based on enumerative search or like learning from past interactions. And we were able to improve the performance of the baseline language model significantly. So thank you.
Great. Fantastic. I think these are really good results. I love it. So next up here, we have Sapient ML, synthesizing machine learning pipelines by learning from human written solutions. And Mukul Prasad will be presenting this for us.
Thank you. Can you see and hear me?
Yes, we can. I believe we will. Yeah, now I can see you. Perfect.
Okay, great. Sorry. Yeah, hello everyone. I'm Mukul Prasad from Fujitsu Research of America, and it's my pleasure to introduce our work on Sapient ML, a technique for synthesizing machine learning pipelines by learning from human written solutions. This work was done at Fujitsu Research jointly with Ripon Saha, Akira Ura, Sonal Mahajan, Chengguang Zhu, Linyi Li, Yang Hu, and Hiroaki Yoshida, and in collaboration with Sarfraz Khurshid at UT Austin. So the problem we are tackling is automatic machine learning, or AutoML, for tabular data. And the aim is that given a user data set and a predictive task defined on it, we need to synthesize a supervised machine learning pipeline that implements that task for that data set. Simply put, an ML pipeline is a sequence of machine learning operators that first processes the data to make it suitable for a learning. This is called feature engineering, and then trains a suitable ML model on it. New data can then be passed through this trained pipeline to make new predictions. The central technical challenge of AutoML is the huge combinatorial space of design decisions, including selecting the right ML components, instantiating a well-formed pipeline based on them, and optimizing hyperparameters for each component. Our proposed approach, Sapient ML, combats this combinatorial explosion using two key insights. The first is that we make the aforementioned design decisions somewhat independently in a kind of divide and conquer approach. And the second is that we learn from existing human written pipelines in a way that allows us to predict the final pipeline rather than explicitly search for it, as most existing AutoML techniques do. So the aim of Sapient ML, as I mentioned, is that given a data set and predictive task, we learn from existing machine learning pipelines for other data sets and tasks to synthesize a machine learning pipeline for this data set. And Sapient ML does this with an offline mining and training step and an online synthesis step. In the offline phase, Sapient ML first automatically mines data science repositories, in our case Kaggle, to create a learning corpus of clean labeled executable ML pipelines paired with their corresponding data sets. From this corpus, it also derives two meta models. The first, shown on the bottom left, is the skeleton predictor, which encapsulates relationships between salient properties of a data set and plausible ML components for its pipeline. And the second one, the pipeline data flow model shown on the top right, captures data flow relationships between components in ML pipelines. In the online phase, given the data set, Sapient ML synthesizes and outputs the best pipeline for this data set based on 3 steps. In the first step, called pipeline seeding, the skeleton predictor is first used to create an abstract pipeline called a pipeline skeleton for this data set. In the second stage, pipeline instantiation, this skeleton is refined into a small set of concrete executable pipeline candidates. And in the third, final pipeline validation stage, these candidates are evaluated to output the best pipeline. We evaluated Sapient ML on 41 benchmark datasets, including 10 new complex datasets drawn from Kaggle, and compared against 3 state-of-the-art AutoML tools, namely Teapot, AutoSKLearn, and AL, as well as 4 baselines, using 3 metrics spanning predictive performance and application scope. For predictive performance, we counted the number of datasets on which a given AutoML tool outperforms all other tools statistically or numerically, tabulated as number of champions or number of winners, respectively. And for application scope, we counted the number of datasets where the tool fails to generate a viable pipeline. The fewer failures, the better, of course. Briefly, Sapient ML outperforms the other 3 tools, first in terms of predictive performance by securing the highest number of champions and number of winners, shown as the blue and orange bars, respectively, and also in terms of application scope by securing the fewest number of failures, in fact, no failures, shown here by the gray bars.
So I think we're just nearly out of time.
And I'm done. Thank you very much, and invite you to read the paper and look at the full presentation. Thank you very much.
Great. Thank you. Thank you. Impressive work. And finally, here we have stack preserving interprocedural slicing of WebAssembly binaries, and presenting that will be Quentin Stephanout. And you can take it away.
So this paper is about slicing, and this is research that has been done in collaboration with Dave and with Koen that are present today. So this is about WebAssembly, and so WebAssembly is this new binary format that you can use, and for example, you can compile applications written in high-level language into WebAssembly. You can integrate them in web applications. So for example, on Google Earth, you have an application that is built partly in JavaScript and partly in WebAssembly. So WebAssembly enables you to offload compute-intensive parts of the application to a more effective engine. And so WebAssembly applications have been used in the past for malicious purpose, and so we need to be able to do some reverse engineering of them. And one approach to do that is slicing. And so that's what led to this paper. We want to do program slicing for WebAssembly. And so program slicing, in a nutshell, it's about computing a minimal version of a program to preserve a slicing criterion. So here we have a program on the left And it's a program in C that computes a sum and a product. And suppose that you are only interested in knowing the behavior of that highlighted line. So this line is what we call the slicing criterion, and a slicing approach will give us a minimal version of the program that preserves the semantics for that line. So the idea then is, can we do this for WebAssembly? So first we'll look at what you call the WebAssembly validation requirement. And for that, we'll simply execute a WebAssembly program and look at what the stack looks like as we execute this program. So here I will simply step through the instructions. So WebAssembly is a stack-based language. So we have a stack and instruction manipulate that stack. So in the first instruction, we have pushed the first argument of the function on the stack, and you can see it on the right. As we do an if condition, we remove that top value on the stack, we inspect it, and then, for example, we can go in the then branch of the if. Then we have a few more instructions to push more values on the stack. We have an instruction that adds two value, so it takes the two top values of the stack, adds them together, and push the result on the stack. Then you can have like a call instruction that will, for example, call a function which expects one argument, computes something with it, and produces one value. So you still have that return value on the stack, and then you drop it. And so the validation requirement of WebAssembly states that, for example, both branches of an if should result in the same stack layout. And so here we end up with an empty stack at the end of this if branch, and in the other branch, which is empty, we have nothing on the stack also. So now let's look at the same program, but this time we'll try to compute a slice. So for this, we can apply the usual slicing techniques that simply follow dependencies. And so suppose you are looking at the slice with respect to this highlighted instruction as a slicing criterion. So because it's an add instruction, we need two values. So we'll need to add the two previous instructions as part of the slice. For this part of the code to be executed, we need the if instruction. And for the if instruction to execute, we also need the condition. So here we have what we could call a closure slice for a program. The problem is that if we try to execute it, it will fail. And that's because we have left one value too much on the stack in our if branch. Moreover, if we try to load this program into WebAssembly Analyzer, for example, this will also fail to load because this is not a valid WebAssembly program. And so in this paper, the answer we provide is an approach to slice WebAssembly binaries and to result in executable slices. And this is done in 3 phases. You can find the details in the paper and in the full presentation. But the idea is that we have a first slicing phase, which computes a closure slice, like I explained. And so this gives you a slice which is potentially invalid. And then we have a reconstruction phase where we fill in locally, we replace the instruction that we removed by instructions that have the same effect on the stack. And so by then we have a valid WebAssembly slice that can be executed and that preserves the semantics for the slicing this criterion. So we have implemented this approach. You can find the artifact, and we have also evaluated it. I will quickly sum up some of the resource questions, but basically we have evaluated it on almost 500 million slices coming from real-world programs. And on average, the size of the slices is 50, 52, 53%. That's lower than similar work doing slicing on binaries, not on WebAssembly binaries. And the sizes are computed quite quickly. So to sum up, we have an approach that works in 3 phases that first computes the slice and then reconstruct the slice. We have implemented it and evaluated it, and you can easily find the implementation online. Thank you.
Great. Thank you so much. Yeah, I really enjoyed that paper because I think I have some colleagues of mine who would directly benefit from the work that you've been doing. So that's great. Okay. Great. So now we can shift to the Q&A part of this. I'll start with questions that haven't been answered, weren't answered in between. So first up, Fernand says here, thanks for your talk and great work. In light of the earlier keynote and in general with the growing and justified concerns around data privacy, including data privacy and research, did you consider potential negative side effects from learning from corrected user code? That is, do you clean or anonymize user data? Can users opt out of this collection? there are trade-offs here, in terms of ethical handling of data and actually getting the results that we need. And I'd love to hear your thoughts on ethical data collection.
Right. Yeah. So, for the purposes of our experiments, we collected the data through an internal hackathon that we did at Microsoft Research India. So, in the hackathon, we basically asked for consent from the users appropriately. But in general, I do believe that the data should be appropriately anonymized. At the same time, for our pandas use cases, the kind of learning that we do is at the syntax level and independent of the user, the semantics of the programs. So we learn syntactic transformations, which should usually be fine.
Gotcha. And great. So the next question that I have here, and I know that Joseph, you answered it in part in the chat, was, Joseph, have you identified conditions under which this dynamic update might not be possible, or that it might not work as well as expected? If you wanted to elaborate on that.
Yes. So of course, there are cases the update is not possible, and I also mentioned that we add a requirement of the switching state to satisfy some switching condition, and of course, sometimes the switching condition cannot be fulfilled. So we saw some examples in our evaluation for update that are not possible, and in this case, in the implementation, we just state that the update is not possible. And an important point here is that it doesn't mean that the update is not possible in any situation. It just means that in the current state, the system cannot force the update, and it is a matter of luck. Maybe the environment will take the state to another state from which the system can force the update, but at the moment the update is not possible. The system cannot force reaching the switching condition and update the specification.
Gotcha. Great. So the next question that I have here, and this is for all panelists. So both program synthesis and reverse engineering problems involve really solving a problem of subjective human comprehension. So the user of the tool needs to be convinced that the outputs you're giving them are credible, that they're accurate, that they match their needs and expectations. Josef's user, for example, can rely on some amount of provable correctness. Hong's user can see a working application running on some device, or Mukul's user can inspect the pipeline. They can inspect the model, right? But what does the future hold for these tools with respect to conveying that trustworthiness, right? What can we do to inform users about what these outputs are, that they work? I'd be curious to get people's thoughts on how we could approach these problems.
Yeah, that's a great question. If I can chime in on that.
Of course.
So at least for our approach, that is a central question, and the way we've built our approach, it's naturally interpretable. So we, in fact, not reported here, but we have other work where we synthesize a multimodal explanation to go with the pipeline, and then the pipeline, of course, is executable. And so we execute it. We report an predicted score on the test data. So both those things. So we can synthesize an explanation to go with it, textual visualizations to explain the pipeline, and it's executable. So it's a key thing. It's a key feature for any synthesis technique, I believe.
Mm-hmm. Anyone else? Your thoughts? How does your tool convey trustworthiness, credibility, right? People have to trust that it works.
Okay, can I say something?
Yeah, of course.
Okay. Yeah, indeed, that's a good question, because some part of our users are any user without any development skills. So that's an important question for us. And I think the only answer to this question is that we have to gather a bunch of users for us to improve the tool. Specifically, our tool does not support any styles. So on the first glass that the users may do not like our server-side companions. So we need them to help us to add CSS to add styles and make them like this tool, like the synthesize app, and help us to improve, give us feedback to improve the tool so that they can trust our tool and use it to synthesize some companions.
Mm-hmm.
Yeah, because our users, some of our users are just end users. So yes, that's a real problem that we are facing.
Mm-hmm. And Joseph, I think this is also something that's very much a concern to your work as well, about trustworthiness and credibility. I work with people, for example, with industrial controllers who use industrial controllers and autonomous robots and other things like that, right? And if those things aren't handled correctly, they could kill people in an industrial setting, right? Like if it's a robot, right? So I'd be curious to get your thoughts on just on the how do you show like this solution's going to work? You can trust it.
So actually, we have another work of another person in our research group that allows the user to define tests and cover some scenarios, specific scenarios of the execution to check that they fulfill the conditions and what the test was supposed to do. So we also try to make the option for testing of the user for him to convince that the coverage covers the conditions.
Right. Ah, gotcha. Nice. So I have a question here in the chat for Joseph. Follow-up question was, does your, sorry, a little bit of a cough. Does your research also recommend the state from which the spec can be successfully applied? As a follow-up question to the earlier one.
Yeah, so no, the current work does not do that, but we actually suggested for future work to maybe extend the work with something like a cooperative environment. So there are cases that the system cannot force the update, but maybe we can use the help of the environment and for a short duration, use the environment to reach a state from which we can update. So that's something we suggested for future work. But currently, we do not do that in our work.
Gotcha. So there's room for future work here. So I have a question here from Monsieur Nassif. To whom is the question directed?
I think it's for me.
Oh,
I'll just
okay.
maybe speak up. Yeah.
Yeah. If you want to ask a question, Matthew.
Well, yeah, I just had a follow-up that already read in the chat. But yeah, I thought it was interesting to think about syntactic versus semantic learning, and then I wasn't sure how that distinction was made.
Yeah. So when I said syntactic transformations, I meant that we are learning. Like most of our transformations are about some syntactic mistakes, for instance, about missing parentheses, missing negations, etc. So usually they should be fine, but of course, appropriately collecting the data is necessary, and that we should definitely take care about. I would like to make another note that the main motivation for Jigsaw-like approach and learning from feedback was that in same software teams within, for instance, a company, there might be multiple users that might be asking similar queries. And in that case, it would be really useful when the user fixes from the first user in the same team helps the second user. And in such cases, hopefully, if the users consent to data collection, then such kind of learning would anyways be very useful. And even the kind of functions that people are using, they should go out and help the users.
That makes a ton of sense. Thank you very much.
Yeah, sure.
So on that note, with Jigsaw, I am curious about with regards to future work. So I know that there's Google, there's a bunch of new work coming out, kind of GPT-3 successors and so on. I know that Google has like Pathways, for example, and these newer models, as you keep throwing more compute power at them, they seem to get more and more powerful when it comes to this sort of highly contextual reasoning, right? What do you think that the future holds with regards to program synthesis in this space?
Right. So I think the main motivation for Jigsaw is still that the vetting process will always be there. And that is the front where we can use like programming synthesis and repair-based ideas to actually help the users and make them productive. So there was this recent study from NYU where they suggested that 40% of the suggestions made by GitHub Copilot had vulnerabilities when tested on an adversarial data. So like, in fact, our current work, we are trying to target such a scenario in which we are trying to learn security repair transformations to reduce vulnerabilities in the generated code. So yeah, I do believe that these kind of approaches would always be necessary for vetting. Moreover, we also feel that they might help us develop a feedback loop where the fixes that are made by Jigsaw can be used to further fine-tune the model and improve its performance.
Yeah, great. Yeah. Do we have other questions that people want to ask in the chat? I know there's some follow-up here, discussion on questions. And yes, but to your point, Naman, as I said in the chat, if it delivers human-level performance, with or without vetting, if it's just as buggy and as unsafe as a human would write, I mean, isn't that successful?
Yeah.
Or are we asking too much of ourselves?
Right. Yeah, that's a fair question. But yeah, for deployment scenarios, you still need some kind of
course,
verification. Yeah.
Mm-hmm.
Should I type the question or just ask?
Please, as you have a question for others here, please ask.
This is for Hong for the first Jigsaw paper. I was wondering what your approach does if the satisfiability problem returns unsatisfied. Do you just fail, or do you do some kind of max sat to synthesize a viable application with what passes?
I'm sorry. Did you mean if our synthesis fail, how do we do next, right?
If your constraint satisfaction problem returns unsatisfiable, that if it's unsatisfiable, what do you do? Do you
yes
solve?
Okay, indeed, we have a mechanism that supports users to assign specific design constraints. Yeah, instead of collect constraints from the form, we have a mechanism for users to put their own constraints into the set, and they can get their ideal solution. Yeah.
I see. Thank you.
Okay. Thank you very much.
Great. Any other questions from folks? Feel free to bring them up if you'd like, or put them in the chat for our panelists.
I might have a question for actually probably a few of the others.
Sorry. You could speak up just a little bit, so you're a little soft.
So yeah, I have a question for maybe Naman for the two Jigsaw projects and Sapient ML. Have you considered doing these either approaches, techniques, not necessarily to generate code, but to generate documentation, with the idea that instead of creating code that a developer needs to vet, creating documentation that will help developers write better code in the end, but in a two-step process?
Yeah. So, sorry. Go ahead, Naman.
No, I was just asking clarification on the question.
Basically, what I had in mind is instead of trying to write code and suggest code, write code examples that will help users use an API or create their own machine learning pipeline, but without giving necessarily a single code that will fix everything, just with a more pedagogical purpose.
So could be instructive. Could the could like by providing this answers for like a pedagogical purpose, could it provide like instructive rather than being like the final answer? For example, they say, oh, but have you tried this? But have you considered that? Like, is that how you're trying to frame it? Thinking in those terms?
Yes. Yes.
Yeah.
Better, thanks.
Well, what I would say about Sapient ML is that, I mean, it partly answers your question, and to Reed's original question. I mean, code without explanation is not very useful. So we do generate an explanation that's certainly not part of this paper, but we do provide an explanation because the synthesis process is naturally interpretive. But if you're talking about generating documentation for existing code, that's not the objective of our approach. I doubt we'll be able to do it using strictly our approach, but probably could be done with. I mean, it's certainly possible to do with existing pre-trained language models to go from code to documentation.
So
Right.
Oh, sorry.
So for like for our work, we had the option of trying to do a more interactive evaluation, but yeah, I think that it has always been on our future work for some time now. But yeah, that definitely would be very interesting experiment to see.
Gotcha. Great. So Yosef, you have a question for Tawfiq?
Yes. So I asked what binary architectures you worked with. So I know there are some architectures that are more complicated with this stuff. So I was interested.
So we worked with eventually with 1100 projects, and we used the default architecture that has been used in the program, in the project for. So we don't divide. We didn't divide our dataset into architecture level. We have optimization level wise. We reported the optimization level numbers. So yeah, we have, I think, all of them. Some of them are 16 ARM. Some of them are 32-bit architecture.
Okay, thank you.
Thank you.
Any other questions in the audience?
So I had a question for Mukul.
Sure.
So in Sapient ML, have you like really thought about how you would integrate these, if you would, or how you would integrate these language models for a more interactive synthesis of these pipelines? I believe interactive nature could serve some benefits.
Yeah, certainly. So the interactive use case is certainly useful. The issue is that what we're trying to do is we are trying to go from a data set to a pipeline so we're trying to solve the bottleneck where the user doesn't really know what kind of transformations or what kind of models they want to incorporate in their pipeline. So we're recommending the pipeline. At least in our case, if you have a user who already knows that this will work or that will work, then writing the code for it is relatively less onerous than knowing that in the first place. So we're trying to address that bottleneck. But sure, once you have a pipeline, if the user says try this, we could probably use a pre-trained language model like your approach to create a snippet, plug it in, and try that pipeline. So it could accelerate the subsequent interactive modification of the pipeline.
Makes sense. Yeah.
Great. Opportunities to unify some of these technologies in productive ways. So I have a question here from Kushal for Tawfiq. How did compiler optimizations affect the identification of all the missing pieces?
Yeah, actually, it has a huge impact. It's a task. Like with higher optimization level, it's difficult to find the functions because at higher optimization level, the decompiler also suffers. It cannot produce the right decompiled version also. with on higher optimization level, much variance in the input. So the model also faces difficulties to find inline functions. So in O0 and O1 optimization level, we have a better performance with our tool, but at O2 and O3, the performance start getting lower, but still it's a high capacity deep learning model. So we achieve a reasonable performance. At least we are better than the Ghidra itself and IDX Pro. Thank you.
Great question. Great question. Well, I think we've got 5 minutes left in our session. I think we might have time for one more question, but I just wanted to take the opportunity to thank all of our speakers. These were all fantastic papers. I think the results speak for themselves. I was really, really happy to see all of these here at ICSE this year. So thank you again.
Thank you very much.
Thank you.
Thanks.
Thank you.
Thank you.
All right. Thanks again. Thank you for making this such a great session. Great discussion. Great work. I see a lot of potential here, and all of this research really. I love even just like, but like for me, I love on the synthesized controllers. I know people that could benefit, right? With Jigsaw, I know people that could benefit, like in industry, right? Same with this interprocedural slicing of the WebAssembly binaries. It was really exciting to see. Great. All right. Well, thank y'all for joining.
Okay.
Thanks.
Thanks.
Have a
Bye-bye.
great day.
Bye-bye.
Bye.
Have a great day.